Welcome to The Explainer. Today, we're looking at something that is honestly way more than just a dry list of complex rules and abstract formulas. We are literally exploring the underlying language of the physical world. Organic chemistry is kind of like this hidden code. It builds our cells, it shapes our environment, and it quite literally fuels the modern world we live in. So let's break down this massive topic together and see exactly how the whole shebang works. Okay, let's dive into this. Our roadmap for today is pretty straightforward. We'll be looking at 1. The birth of organic chemistry, 2. The hydrocarbon family tree, 3. Speaking the IUPAC language, 4. Saturated and unsaturated molecules, and finally 5. Natural sources and refining. Starting off with Section 1, the birth of organic chemistry, shattering vitalism. To really appreciate this science, we actually have to travel back in time. So before the 19th century, scientists firmly believed in this idea called the vital force theory, or vitalism. Basically, they thought that organic compounds could only be created by living things, plants and animals. But in 1828, everything completely changed. A German chemist named Friedrich Wöhler took two entirely inorganic compounds, silver cyanate and ammonium chloride, applied some heat, and synthesized urea right there in his lab. And urea is absolutely an organic compound. By creating it from non-living materials, Wöhler literally shattered the vitalism myth overnight. From that moment on, organic chemistry was redefined simply as the chemistry of carbon compounds. Moving right along to Section 2, the hydrocarbon family tree, the carbon alphabet. Let's look at the basic letters of our new chemical language. The undisputed star of the show here is carbon, and carbon has this incredible superpower called catenation. Catenation is basically the unique ability of carbon atoms to join together to form short chains, incredibly long chains, and even full rings. Because carbon has 4 valence electrons, it just loves to bond. This catenation is what allows for what chemists call a homologous series. It's a group of molecules where each member differs from the next by one constant unit. Honestly, it's exactly like adding letters one by one to form longer and longer words. Which brings us nicely to Section 3, speaking the IUPAC language, naming the chains. Time for a quick grammar lesson. So IUPAC stands for the International Union of Pure and Applied Chemistry, and they've given us this brilliant systematic way to name compounds. And this brilliantly illustrates how intuitive it actually is. The prefix tells you exactly how many carbon atoms, represented by the letter N, are in the molecule. If N is 1, the prefix is meth, like methane. 2 carbons is F, 3 is prop, and 4 is but. Once you memorize these simple prefixes, you literally hold the keys to decoding almost any simple hydrocarbon name you ever encounter. Now, naming more complex molecules just requires following 3 basic rules. First, you hunt down the longest continuous chain of carbon atoms. That becomes your parent structure. Second, you assign numbers to each carbon in that parent chain. But here's the trick. You have to start numbering from the end nearest to any branches or side chains. Finally, you name those side chains, using the numbers to indicate exactly which carbon they are attached to. You just separate names with hyphens and numbers with commas. It is a perfectly logical set of rules. It ensures that a scientist in Tokyo and a scientist in New York write the exact same name for the exact same molecular structure. Let's jump into Section 4, saturated and unsaturated molecules, bonds and reactivity. This is where we see how these structures actually behave in the real world. Now, what's really interesting about this slide is the dramatic difference a single bond can make. On one hand, we've got saturated hydrocarbons, or alkanes. These have only single bonds between the carbon atoms. They're fully saturated with hydrogen. Chemists also call them paraffins, which literally translates to little reactivity. They are structurally condense and, well, pretty lazy. But on the other hand, we have unsaturated hydrocarbons. These are the alkenes with double bonds and the alkynes with triple bonds. Because of those multiple bonds, they are highly reactive and completely ready to engage chemically. Oh, and there's also a special third class of unsaturated hydrocarbons called aromatics. The defining feature here is the benzene ring. It's this planar, hexagon-shaped ring of 6 carbon atoms that shares electrons around the whole structure, making it highly stable. And yes, they're called aromatic because a lot of these compounds actually have very distinct, sweet, and pleasant smells. Let's see how all this translates to real-world applications, because these abstract names correspond to things we interact with every single day. Take ethene, for example, an alkene with a double bond. We literally use it to artificially ripen the fruit you buy at the grocery store, and it's the monomer we use to make polyethylene plastic. Then there's ethine, an alkyne with a triple bond.
Have you ever seen a welder cutting through thick steel with an intensely hot oxyacetylene torch? That is ethine burning. It's also the chemical foundation for the PVC pipes carrying water through your home right now.
So, these chemicals clearly run our modern civilization, but it begs a massive question. Since we use so much of this stuff to make our plastics, ripen our fruit, and fuel our machines, where do we actually find all these hydrocarbons in the natural world?
To answer that, we have to look underground. Welcome to Section 5, Natural Sources and Refining, Fossil Fuels to Fuel.
The vast majority of our hydrocarbons come straight from fossil fuels: natural gas, petroleum, and coal. And there's a profound historical irony here. Remember how Friedrich Wöhler proved you don't need living things to make organic compounds? Well, despite that massive breakthrough, the hydrocarbons we rely on today were actually formed by the slow, pressurized decay of ancient plant and animal bodies over millions of years, deep underwater. We are literally mining ancient life to power the present.
When we pump petroleum out of the ground, it's a dark, thick, viscous crude oil. Basically, a very messy soup of different hydrocarbons. To make it actually useful, we put it through a process called petroleum refining. Specifically, we use fractional distillation. We heat the crude oil way up, and because differently sized hydrocarbon molecules have different boiling points, they naturally separate out. The heat acts as a giant chemical sorting machine.
This chemical sorting process is basically a perfect summary of everything we've talked about today regarding carbon chain lengths. The lightest molecules with only 1 to 4 carbon atoms boil off first as natural gases for heating. Chains of 5 to 10 carbons give us gasoline for our cars. As the carbon count goes up, the liquid gets heavier and thicker. 10 to 16 carbons, that gives us kerosene for jet fuel. 15 to 18 is heavy diesel. And finally, the massive chains with over 20 carbon atoms, they don't boil off at all. They become the thick, non-volatile solids like paraffin wax for candles or the heavy asphalt we use to pave our roads. The size of the molecule directly dictates its physical properties. But sometimes when we refine crude oil, we end up with way too much heavy, less useful stuff and not nearly enough high-demand fuels like gasoline. So chemists developed a genius solution called cracking. We literally break those long, high molecular mass carbon chains into smaller, far more valuable pieces. We can do this with brutal, intense heat, called thermal cracking, or we can use a chemical catalyst to achieve the same result way more efficiently, which is known as catalytic cracking. It's pure molecular engineering designed to meet the energy demands of society. So, the crucial point is captured perfectly right here. The element carbon is the basis of all organic compounds. It is a single, humble element on the periodic table, but thanks to its ability to chain together endlessly, it creates an infinite alphabet. It builds the structure of life, it builds the medicines that heal us, and it provides the massive reservoirs of energy that drive human progress. We've journeyed all the way from the vitalism debates of early 19th century labs to the massive petroleum refineries of today. We've seen how a few simple rules of naming and structure dictate the physical reality all around us. But remember, chemistry never stops. As we transition away from fossil fuels, the next great frontier will be found in how we manipulate this exact same element. So I'll leave you with this to think about. What new, unseen chemical structures will we synthesize next from the carbon alphabet to solve the energy crises of tomorrow? The language of carbon is infinite, and honestly, we're still just learning how to write with it. Thank you so much for joining me for this explainer.